everybody. Thank you for braving this truly exceptional, awful weather. I imagine no one walked to get here, hopefully. So anyways, welcome. At Great Mountain Forest, we work to ensure that the forests of our region are well cared for and serve their communities in a meaningful way. A critical part of that work is learning from researchers who are helping us to better understand how forests respond to threats like invasive disease and how we can manage them in response. Also, I'm Michael Zarfos, the Executive Director of Great Mountain Forest. I prepared remarks and now I'm actually making a fool of myself anyway. So, we bring you this afternoon's talk, winter lecture talk, thanks to the generous support of series sponsors Molly Ackerley and Michael Sconiers, with additional thanks. Thank you. With additional thanks to Andrew Thompson of Pikeman Studios, doing our VA, and Chris Keys of the Norfolk Library for hosting us. And thanks to Vicki for making the wonderful maple popcorn. If there are any Connecticut certified forest practitioners in the room, see me after the talk for continuing education units. I know that's very exciting for some of you. This afternoon, we're delighted to welcome Dr. Elisabeth Ward, a scientist at the Connecticut Agricultural Experiment Station in New Haven. Her work focuses on forest health and resilience. She leads research on how forests are changing in response to invasive pests, disease, and management decisions. As a part of her exciting master's and PhD research back when she was at Yale School of the Environment, Eli showed that understudied shrubs like mountain laurel, our state flower, and their fungal associates play an important role in forest carbon storage and nutrient cycling, which I think is really cool because I studied forest soils. That's not what this talk's about, but I just wanted to mention it because it's very cool. Her work has spanned rural woodlands, like where we are now, to restored urban forests, which is very cool. We're especially excited that Eli is leading several scientific projects that have sites at Great Mountain Forest, with more potentially on the way. If you'd like to learn more about her work at GMF, please look for the feature article in our upcoming newsletter, which you can sign up for on our website. And with that, please welcome Dr. Eli Ward.
Thank you, Mike, for the excellent introduction. Like Mike said, I am a forest ecologist at the Connecticut Agricultural Experiment Station. I've been working there for about a little less than 3 years now, since May 2023. Like Mike also said, before that I did both my master's and my PhD at the Yale Forestry School, also in New Haven. So even though I've been at the Connecticut Agricultural Experiment Station just for a few years, I've lived in Connecticut for almost 10 years now. And in addition to primarily being a research ecologist, a forest ecologist, I also kind of have this side role that I've taken on at the Connecticut Agricultural Experiment Station, which is being the coordinator for Connecticut's forest health program. So I'm going to talk a little bit about that in addition to my research. And the nature of that role is that I work cooperatively with the Forest Service and surrounding states, because of course a lot of these forest health issues that we're dealing with are not just issues in our very small state of Connecticut, they're issues that transcend state and even national boundaries, and so that's the purpose of that cooperative forest health program. So, I know some of you in the room are very familiar with the Agricultural Experiment Station. I have some of my colleagues here. But who has not heard of the Connecticut Agricultural Experiment Station? Okay, only a few people. So I'll keep it brief. But basically, I like to start my talks by saying what we are, because we're a really unique institution. We're an independent state research institution, so we're not affiliated with any university, but we are a research institution. We're the first agricultural experiment station in the country and the only one that's not affiliated with a university. And so we do tons and tons of research. We have, I think, over 100 scientists and staff conducting research in the fields of forestry and environmental science, entomology, pathology, and analytical chemistry. But then, of course, we're a state agency, so we also do lots of public service, things like soil testing and surveillance for diseases and ticks and mosquitoes. And then we also, the component of public service that I contribute to at the Connecticut Agricultural Experimentation, in addition to my research, is doing our annual forest health surveys. And what this consists of is literally me, let me see if I can do the clicker, literally me flying in this tiny plane across the entire state of Connecticut once a year. So I took on this role 2 years ago, so I've done this for 2 years now. The plane theoretically fits 4 people. I really would not recommend having more than 3 people in there, and even that's a stretch. I'm not that big of a person, and I'm taller than the plane, as you can see in the photo. Anyway, so every year we fly over the entire state of Connecticut, and we map damage to forests across the state. So an example of that is, in this photo you see here, is some oak mortality in the vicinity of Kent, Connecticut, that was caused by multiple years of defoliation by spongy moth, which was formerly known as gypsy moth. And the product that we get from these surveys, which this is part of my role, like I said, of being the Connecticut State cooperator working with the Forest Service to do these forest health surveys, is a map of all the damage across the entire state of Connecticut. And so this year in total, we had 240,000 acres of damage that I mapped across our forests. So this could include mortality, twig dieback, defoliation, discoloration, any kind of damage that you can see from the arid document. And notably, this is, like I said, I've done this for 2 years now, and this is an almost 3-fold increase in forest damage this year that I mapped compared to last year that I mapped. And really the main culprit, which I will talk about today, for this 3-fold increase is beech leaf disease, which has really just taken off, as I'm sure you've all seen in our forests across the state. But this problem is not just Connecticut, of course, as I've already referenced. Pests, pathogens, and diseases are affecting forests nationwide and even worldwide. So this is having a really big impact. Let me see, I put in some stats here. So in the continental U.S., tree mortality from pests and pathogens reduces forest carbon by about 5.5 teragrams a year. And I think I looked this up, and the Empire State Building weighs a tenth of a teragram. So that means every year we're losing like 55 Empire State Buildings worth of carbon. I don't know if that's helpful, but it was helpful for me. And also, in addition, 41% of standing live trees in the continental U.S. are susceptible to invasive pest pathogens and diseases that are already present in the United States, which is also really shocking and terrifying. And then, of course, here in the Northeast, we're particularly susceptible just because we have a really large number of invasive pests and disease for multiple different reasons. Of course, we have the biggest metropolitan area in the country, so that means there's a lot of movement and globalization, there's a lot of suburbanization, there's a lot of forest cover, there's a lot of tree species. All of these things have really meant that we have the most number of invasive pests and diseases in this region, and so our forests have been really heavily impacted. So given the scale of this issue, particularly in our region here in the Northeast, as Mike introduced, a lot of my research these days at the Agricultural Experiment Station focuses on how we can improve forest ecosystem health in the face and in the aftermath of damage from these different pests, pathogens, and diseases. And I've told many of you this already, but in putting this talk together, I struggled because I know we have a very broad audience, ranging from my mom to my supervisor. So I'm going to start with a little bit of background to get everybody on the same page. So So like I said, a lot of my work these days focuses on forest ecosystem health, and one really useful framework for thinking about and assessing forest health is this idea of forest resiliency, which I'm sure many of you are already familiar with. And so the classic definition in my field, at least, is of forest resiliency is the ability of an ecological system to recover its properties after being altered by a disturbance or intense and continuous stress, such as tree mortality or damage from invasive pests and pathogens. So in this example, we have mortality, and then following that mortality event, we then have tree regeneration, so seedlings coming up in the understory, and forest regrowth. And so that would be a highly resilient forest to that particular stressor. And then the opposite of that would be a low resiliency ecosystem in which we had that same kind of stressor, and instead of regenerating, the seedlings coming up, forest recovery and regrowth, we get proliferation of understory plants, and ultimately tree regeneration failure, and the forest doesn't really recover in the same way or provide the same ecological functions or services. So in thinking about forest resiliency, there are lots of different components and definitions, but when I think about it, I kind of simmer it down to a couple different factors, which I'm going to talk through right now. The first being tree species diversity. Higher forests that have higher species diversity generally are more resilient, because if you lose one species, you have a different species that will kind of take on the same functional role. Versus if you have just a single species across the entire landscape, a lot of what we see in the western US forests, with just one conifer species being wiped out, then you have a much less resilient system. And then the kind of other facet of this is that's similar and related is, in addition to tree species diversity, having forest age class diversity similarly kind of gives resiliency at the ecosystem scale to some of these stressors, because some of these stressors impact forests that are older, some impact forests that are younger, but most importantly, these different forest ages have different species, and so by keeping all the different forest ages, we're able to keep all the species on the landscape and have a more resilient system. So I'm going to talk about just these two different components of forest resiliency that I am referring to in this talk, just within the context of Connecticut and what we have going on with our forests here. So for the first, thinking about tree species composition and diversity, Connecticut is a very forested state. I think it's tied as the most forested state that also has the highest population density. I think Massachusetts and Connecticut are tied. So it's very impressive given just how many people live in Connecticut, how forested we still are. And I'm going to walk through the most abundant tree species in Connecticut, but I'm also going to talk about two different metrics of abundance when I talk about the most abundant tree species. And the first meaning the most abundant tree species in terms of total volume in the forest. And so you're more abundant if you have a lot of wood in the forest, and those tend to be our classic canopy trees, the forest types that we think about most common. And so the most abundant species by volume are maples, red maple, red oak, black oak, white oak, black birch, and white pine. And the other way to think about the most abundant tree species in our forest is by literally the number of different individuals. So instead of the species that are taking up the most volume, there might be a few individuals, but they're really, really big. You can have just tons and tons of individuals kind of in the mid-story and understory. And this is another metric for thinking about the most abundant species. And these include red maple, black birch, American beech, sugar maple, white pine, and eastern hemlock. But going back to the idea of resiliency and thinking about how the forest composition in Connecticut is changing amidst all these stressors that I've started to talk about, what I think is interesting is to compare the most abundant species in terms of volume and stem count, because it gives us an indication of how our forests are changing. And so, of course, we have some similarities between the two, but we also have some differences. Most notably, all of the oak species are the most dominant species by volume, so they are the dominant canopy species in Connecticut, and it is true that most of our forests are classified as the oak hickory type. But we're not seeing them in the most abundant species by stem count. Instead, we're seeing these other three species, American beech and sugar maple and eastern hemlock, all of which have one very important ecological trait in forest ecology in common, which is that they're really shade tolerant. And so they're trees that can grow up in the understory as the prevailing canopy trees over time, they die over time, they can replace it and become more dominant. And so the reason these three shade-tolerant species are the most abundant in terms of number of individuals is because there are lots and lots in the midstory and understory across our forests. So in the absence of kind of like all these other stressors I'm dealing with, we're talking about invasive pests and pathogens and all the other ones that I haven't even mentioned. We might think that our forests would be shifting more from this oak-dominated ecosystem to some of these shade-tolerant species, particularly things like sugar maple. And it is true, and this is not just in Connecticut, there's a general trend of oak regeneration being in decline, in a large part because many of you may know this, but oak being so dominant in our landscape is really a legacy of the past land use history in our region. So widespread use of fire from indigenous peoples, but also colonial land clearing, and really open growing conditions that promoted the dominance of oak, which requires really high light in order to grow and become the dominant canopy species that we see today. And so naturally, our forests are transitioning, like I said, to those more shade-tolerant species. So if we want to keep oak and some of the other shade-intolerant species, the ones that require a lot of light, we really need to do some kind of active management to have both these closed canopy forests, but also more open growing conditions that some of these other species can regenerate in. Which brings me, like I said, the two different factors of forest resiliency that I think about are connected to my second factor of forest resiliency that I'm talking about, which is forest age class diversity. So in Connecticut, this is a little bit outdated at this point, but this is a bar chart from the Connecticut Forest Action Plan, which was written in 2020 and will be updated again in 2030. But it shows the distribution of forest age classes across the state of Connecticut. And you can really see that most of the forests in Connecticut are in this one homogeneous maturing age class. And the younger forests and the older forests are underrepresented. And once again, this is a product of the past land use history in our region, is that a lot of the land was cleared for colonial use, all of the by European colonists for agricultural use, and then when those forests regrew, they all regrew around the same time and became the same age. So going back to my the connection between managing for forest and age class diversity and tree species diversity, this is once again somewhat problematic from a resiliency perspective, in that our younger forests have a completely different suite of tree species that are associated with them than our older forests that have some of those more later successional species. And so once again, this really goes into the idea of resiliency is thinking about promoting diversity, and in order to do that, you need both the stand age class diversity and tree species diversity. So diversifying the forest age class diversity should help us maintain that full suite of tree species in Connecticut. Okay, so now that I've given a little bit of background about how I think about resiliency as a tool for thinking about how we can improve forest health in the face of some of these stressors and challenges we're dealing with, I'm going to talk about a couple of different case studies of research that I'm now conducting as part of my program, focusing on emerald ash borer and beech leaf disease. So the first I'm going to talk about about is emerald ash borer. How many of you are familiar with emerald ash borer? Yes. Okay, so I'll be really quick, but just to have everyone on the same page. So emerald ash borer has been around for a while now. It was first detected in Connecticut in 2012, and so we've all been witnessing its impacts for over 10 years now, and the massive amount of ash mortality that we've seen, especially in this part of the state, to be honest. And another scientist at the station has been monitoring, that has been at the station for much longer than me, has been monitoring the population dynamics of the emerald ash borer insect itself. So she's an entomologist versus I study more the forest plant responses. And so like I said, it was first detected in Connecticut in 2012 in northern New Haven County. You can see it on that little map right there. And the cool thing about her work is that she found that after 3 to 5 years, that's when the population of emerald ash borer peaked. And so once again, you can see on the map right there in northern New Haven County where you're getting that population peak. But the even cooler thing is that she found is that after 9 years, the population started to crash. And this is, of course, really intuitive to many of us, because if you're a pest that is killing off a host that you depend on, at some point there's no longer going to be that host there for you to eat, and so your population is going to crash. And so a big question now, longer term, is thinking about whether this pest is going to rebound when all the regenerating ash seedlings kind of in the understory become big enough that it can attack it, or whether those seedlings can rebound and become a kind of a functional part of our forest again. So to start addressing some of those questions related to how our forest dynamics and composition is changing in response to emerald ash borer invasion, given all this data that we already had through another scientist program at the station, I set up a project. This is the first project I set up, looking at how overstory ash mortality across the state from emerald ash borer is affecting understory plant communities and tree regeneration. And so in particular, what I was interested in, going back to that idea of forest resiliency, is whether we have a system that's resilient to this stressor, where we're getting a lot of regeneration and the forest is developing after it, or whether the forest is kind of succumbing to these understory plant invasions. And I also, Mike alluded to this briefly, but I did do my PhD in forest ecology, and I wanted to throw forest soil ecology, and I wanted to throw a little bit of soil stuff in here as well. So in addition to this, I was also interested in testing a hypothesis related to soil conditions and whether soil conditions could be predictive of whether we're seeing these forests succumb to understory plant invasions, or whether we're getting a lot of tree regeneration and forest development. So my hypothesis was, of course, that overstory ash mortality is going to cause these canopy gaps that are going to increase light availability, and that will, of course, promote forest regrowth. That plants need light, and so there will be plants that grow. And then my hypothesis related to soils is that under higher soil resource conditions, such as higher soil nitrogen availability, the invasive plants, which tend to go super fast, as we all know, they're going to be able to outcompete the native species in the tree regeneration. Versus on the contrary, the sites that have higher soil carbon availability, which tends to be associated with lower resource conditions, lower nitrogen availability, those are the conditions in which we see more tree regeneration, a higher diversity of native plants coming in. So this was my ecological hypothesis related to what our forests were going to look like in the aftermath of emerald ash borer. So, like I said, we then set up plots across the state of Connecticut using that data from Dr. Claire Rutledge at the station. We set up 81 forest inventory plots that captured all the years of time since EAB detection. So all the way from 2012 in the red spot in the middle, in northern New Haven County, all the way up into the far corners of the state, like here, that were invaded later. And within each of those, we had 27 sites, and within each of those sites, we also set up 3 different plots that varied in overstory ash basal area, or the abundance of overstory ash, basically to get the different light availabilities. So if you only have 1 ash in the overstory, you're going to have a really small canopy gap, versus if you have a bunch of ash, you're going to get a bigger canopy gap. So once again, thinking about these resource gradients, both light and soils, and how that impacts understory plant communities and tree regeneration. All right, and here's what we found. I should also say this is work that was done in large part by Jack, who is my technician, and this was his master's thesis, and he's in the audience today, so thank you. All right, so here's what we found. So just to orient you on this graph, we have non-native plant cover on the y-axis, and then the proportion of dead ash on the x-axis. So moving further to the right, you're getting a higher, you're getting bigger canopy gaps that were created from dead ash. And as you can see here, we have a positive relationship between the proportion of dead ash within one of our plots and non-native plant cover. So more dead ash, more invasive plants. And then in the contrary, so this is the same plot setup. We have the proportion of dead ash on the x-axis, and native seedlings now on the y-axis. So this is the seedling regeneration that we're looking at. We're seeing a decline in native seedling regeneration with bigger canopy gaps. And this is a little bit counterintuitive, because usually you get bigger canopy gaps, more light, means more forest regrowth. But because we're seeing an increase in non-native plant cover, it could be that those non-native plants are outcompeting the native tree seedlings. So together, this data is really suggesting that forest composition in the aftermath of emerald ash borer invasion is really shifting towards a higher abundance of non-native plant species and a lower abundance of native tree regeneration, suggesting that these forests are not resilient to this stressor in the absence of any kind of active intervention or management, such as invasive species control. Okay, so now we're going to get into the soils part for the ecological hypotheses. And we found, which is similar to our hypothesis, that soil nitrogen availability was really strongly and positively associated both with non-native plant cover, which is the graph on the left, and non-native seedling regeneration, which was mostly, in this case, burning bush. And so, like I said with my hypothesis, the idea was that under these really high resource conditions, which ash tends to do really well in really fertile, mesic, moist sites, these non-native plants are able to kind of outcompete the native regenerating trees. Okay, here's another graph. All right, so this graph, I'm going to walk you through it, don't worry, but this is showing the community composition of the whole understory plant community after emerald ash borer invasion. And we've highlighted on this graph the 9 most abundant non-native plants, because they were the only ones that fit, and the 10 most abundant native plants. So you can see kind of a separation in the community composition where the non-native plants are versus the native plants. And then the blue arrows, which I'm going to highlight in a second, are the different environmental factors that are associated with the different plant community compositions in these sites. And so we see that these are highlighting what the blue arrows are saying. We see that the non-native species tend to be more associated with, once again, just like our other graph showed, higher nitrogen availability and higher overstory ash mortality, versus native species. The top 10 native species in general were associated with higher forest cover or live tree biomass, and also higher soil carbon availability. And then just the top most abundant native and non-native species are shown here. So once again, this kind of affirmed our hypothesis of higher soil nitrogen availability being associated with more invasive plant cover. And also we found that lower soil carbon availability was associated with lower non-native plant cover. And also non-native plant cover was associated with higher ash mortality. So altogether, these results from this really exciting project suggest that some kind of proactive forest management may be needed to restore these forests and promote forest health in the aftermath of emerald ash borer invasion. So this includes things like invasive plant control and active forest management called regeneration harvest to increase light in the understory and kind of promote tree regeneration. So the next steps for this project, which we're currently working on, are that we also, in addition to all of those currently unmanaged ash sites, which is the data that I've showed you right now, we sampled in the past 2 years, I think, 11 different ash salvages, so areas where prior to emerald ash borer invasion, foresters went in and cut ash before it died to recoup some of the economic value. But most of these instances, they also created bigger canopy gaps to try to promote regeneration in the understory as well. So we sampled these different ash salvages, including 2 at Great Mountain Forest, and we're currently analyzing that data to see how that impacts tree regeneration and understory plant diversity. And then we're also hoping to, in the future, secure funding to help do some invasive control in these forest sites that are really, really heavily invaded to try to promote regeneration and restoration of these forests. And finally, like I alluded to a bit when I was showing Dr. Claire Rutledge's work, we do plan on going back to these plots in whenever I feel like it, but maybe like 5 years or so, because the understory of the forest is completely carpeted with ash seedlings. And so there's a lot of really negative, sad things that I end up saying in this talk, and so I always like to put this slide up because Dr. Rutledge did find a bust in the population. There are tons of ash regenerating in the understory. There is the potential that this cohort could regrow and become a functional component of our forest again. It just requires the long-term research, which we're doing to assess whether the species will rebound following the EAB population crash. And the other thing I like to conclude about the emerald ash borer component of the project, and this is kind of a thesis of this whole talk, whenever I give like management recommendations, that's for one site or some sites, but we really need to be doing lots of different management strategies in different places in order to promote kind of forest health and forest resiliency at the full state scale or full region scale. So if I'm saying like we should promote more active forest management and ash salvaging, like yes, we should do that in some places that may be super susceptible to an understory plant invasions to get regeneration there. But we also need to do other things simultaneously, in particular scout for potential lingering ash that may be resistant to emerald ash borer, and while simultaneously working to continue to suppress the EAB population through biological control, which is something that Dr. Rutledge does as well. So lots of different management strategies and lots of different places, not just one solution. Okay, so that concludes the emerald ash borer part of the talk. So now I'm going to move on to, I think, usually I invite people to ask questions, but I think I'll just do the whole thing and save room for questions at the end. Now I'm going to move on to this new disease, which is very different from emerald ash borer, and a lot of the research is, I'm setting up lots of new projects related to beech leaf disease, and I don't have quite as many results, but there's a lot of questions to answer given how novel and devastating this disease has been. So Beech leaf disease. Who's heard of it? I'll do the same thing. Okay, so beech leaf disease has been around in Connecticut since 2019. It's been in the U.S. Since 2012. It was first detected in Ohio in 2012. This is the map as of December 2025, so just a month ago, of the current distribution of beech leaf disease. So you can see in 2012 it was first detected in Ohio, but there's a pretty big lag between when it was first detected in Connecticut in 2019. But when it was first detected in Connecticut in 2019, it really shot off, and within 5 years, the entire Northeast was invaded by beech leaf disease. So what is it? Beech leaf disease is a foliar nematode. I gave this talk once to an audience that included my husband, and he made fun of me afterwards and said I had to define what a nematode is. So I will do my best and say that it is some kind of microscopic worm. And there's a picture right here of what it looks like, a cross-section of the inside of a leaf. Basically just this proliferation of so many microscopic worms, attacks of microscopic worm. And then, as you all know, this is kind of what it looks like in the early stages, where that microscopic nematode is within the leaf, and you can see this dark banding. At this point in Connecticut, the symptoms are so severe, as many of you have seen, that we really get crinkling and leaf loss, and then the trees kind of put on a second flush of leaves to try to support their growth, given what they're experiencing in their leaves. Like I said, this is a very new disease. I usually have a lot of questions about beech leaf disease. That's what the newsletter that Mike referenced, that's the newsletter article that's coming out that I was interviewed for, was talking about beech leaf disease. There are a lot of unknowns. One unknown is what's causing the spread of it. There are a lot of hypotheses, but we still don't really know. But what is noticeable is that we're really getting this, we're seeing the spread going up into the Northeast, kind of along the eastern seaboard, following the prevailing wind direction. And then there's also been some work that's shown that it's really tightly associated with water droplets. And so one hypothesis is that kind of the prevailing wind, rain, storm systems are what's driving it up along the East Coast, deep into northern Maine. First, as you will notice that southwestern Ohio doesn't even have beech leaf disease yet, even though it was detected in Ohio in 2012. I usually get a lot of questions about beech leaf disease, but I can save those for the end. So like I said, there are a lot of really just basic unknowns about beech leaf disease, given how new it is to our country and our state and our region, and how quickly it's had an impact. It's really quite unprecedented. To my knowledge, there's never been an invasive nematode before, so it's just leaving a lot of questions about what do we do about this, what is it? And so one of the first things that we started doing, and I did this, so Dr. Jeff Ward is my predecessor in this position, and he has the same last name as me, but he is not related to me. I always need to say that because he's on the board of trustees, and so many of you probably know Jeff. Not related to me. Anyway, one of the first projects I set up when I started the station, and this was with Jeff this was in collaboration with Jeff, is we started continuously monitoring all the beech trees that were on any of the long-term forestry projects that he set up in his entire career, basically. And so this is one of the great things about the Agricultural Experiment Station. I feel really privileged to work here. Last year was our 150th anniversary. For most of that time, there's been some kind of forest ecologist in this position, and so there's just really great long-term forest data that's needed to ask super basic questions like, what are the impacts of beech leaf disease on tree growth and mortality when no one's ever seen it before? So Jeff and I set up this project when I first started of just going and doing a quick, we call it a rapid assessment annual remeasurement of all of the beech trees in his long-term plots. And this includes some plots up at Great Mountain. And the results are not that surprising, especially now that we've seen it progress for a few years. But it is good to document just how high the impact it's having on tree growth. But basically, of course, we saw beech leaf disease severity increase rapidly across the entire state. And so this is a graph that Jeff put together that includes the data from this year that is showing the really rapid decline in tree growth. Annual diameter growth is what's on the y-axis. And the 4 different colors are the different crown classes of the trees. So dominant are the upper canopy trees. Intermediate are the intermediate canopy trees. They're getting some shade, but they're not getting as much light as the dominant ones. Co-dominant is slightly below dominant, and suppressed is in the understory, so getting no crown light exposure. And so because beech leaf disease is affecting the leaves, it's causing the leaf curling and leaf loss, the trees that are getting more light in the upper canopy should be doing better than the ones that are getting no light in the understory, because beech leaf disease is affecting the photosynthetic capacity of the tree. So we do see that a little bit, but that shouldn't be the takeaway of this graph. So you can see the dominant individuals, those upper canopy ones, had maintained a slightly higher growth rate in the beginning. The main takeaway is that regardless of where you are in the crown position, your growth rate is basically stagnating. So the other thing we looked at, because of course Jeff has an entire career of forestry projects that involve active management, is we looked at the impacts of some of those different forest management practices on how beech leaf disease was affecting tree growth and mortality. And once again, so this is the second graph here, so we have the different years over time, and once again, annual diameter growth. And in this case, he looked at sites where we had no release of the trees, so the trees were just still surrounded by trees, they weren't getting that much light. 1 or 2 sides of release, so there was some kind of forest management practice that increased light on 1 or 2 sides of the tree. And then the purple line is 3 or 4 sides of release. So once again, some kind of management practice that increased light on 3 or 4 sides of the tree. So as you might expect, we are seeing these slightly higher growth rates in the trees that were released, so they're getting more light. But once again, this is really the big takeaway isn't the small difference in growth between these lines. The big takeaway is that regardless of how much light you're getting, your growth is really just plummeting. And so we've been doing this monitoring now for at least 3 years. And we're seeing this stagnation of tree growth across all crown classes. But really the surprising thing, at least in our plots, I've witnessed different things in some other forests, is that in these plots we're not seeing any widespread mortality yet, which is interesting. And one thing that I think might be the reason that we're not seeing such widespread mortality despite this really severe impacts on tree growth is that beech is a clonal species, and so if you're in a stand that has tons and tons of beech, like this one, it's very likely that all of those beech are all connected via their roots underground and all sharing resources with one another. And so because of this, those upper canopy trees that are able to get a little bit more light can kind of subsidize any decline to the understory trees that aren't getting as much light. And so it takes a lot to kill something. And so basically what Jeff and I are thinking is that there will be one year that there's a drought, or it's just been too many years of this really slow growth rate that'll be kind of like a tipping point for an entire stand, rather than just seeing one tree die here, one tree die there, which is more like emerald ash borer. So I have a bunch of new projects that I'm setting up to try to think about how we can improve forest resilience, forest ecosystem health and resiliency in the face of this disease that, of course, is causing these really severe impacts on our forests. And just looking at this picture and everything I've talked about in this slide so far, I think this really shows just how not resilient these beech stands are to this type of stressor. We're seeing absolutely no regeneration in the understory, and that's because beech is a very shade-tolerant species, which also means that it casts a lot of shade in the understory. So really, not that much grows in the understory at all. So what happens to a stand like this that has tons of beech, nothing growing in the understory, and then all of a sudden the entire canopy dies back? I paid a visit to a site that I'm working on out on Long Island, and I think they must have gotten hit by beech leaf disease just like 1 year before Connecticut or just slightly earlier, because we're already seeing much more pronounced canopy mortality. This is all anecdotal, not database, but much more pronounced canopy mortality out on this site on Long Island. And this is what some of the sites look like, but basically any sites that were had any moisture at all. This is a super sandy forest, very high deer browse, that's why we're seeing very little regeneration. But at pretty much any sites that had any kind of moisture in the understory had this thicket of annual weeds. And so there's no trees regenerating, the canopy is thinning, and we're just getting these annual weeds coming in. Once again, just kind of reiterating that these forests are potentially not that resilient to overstory tree decline from this very new pest. So one project that I set up last summer and we're now implementing the treatments for, so it's in its very early stages, is a project in urban and community parks in and around New Haven, which is where the agricultural experiment station is based. And a lot of these parks are like that stand in this last picture, where they're just completely monodominant beech stands. And particularly in the context of urban parks, this is really an issue because, of course, urban areas have a ton of invasive species pressure. And there's nothing in the understory right now, so what will happen if we just wait for the beech to die? Is it just going to get completely overtaken by invasive plants right away? And so we're working together with the Parks Department in New Haven and implementing some proactive forest management treatments that we're testing to try to get ahead of that potential issue and promote tree regeneration before the beech actually dies. And so the different experimental treatments include, of course, no beech canopy treatment, so the control. Beech canopy treatment, so we're actually treating the individual beech trees with a bark spray. It's a phosphite bark spray to help mitigate beech symptoms. And then the third is beech canopy removal to try to create these canopy gaps that could promote light in the understory. And then of course, across all of these treatments, because deer browse is such a huge issue in tree regeneration, especially in southern Connecticut and southern New England, we have parts of these treatments that are fenced and unfenced, once again, to try to get that regeneration. So that we took the baseline measurements for that project last summer, and we are implementing the treatments now and throughout the spring, and we'll see where it goes from there. But same with what I said about the emerald ash borer project. Once again, we're not trying to cut down all of the beech forests everywhere just because there's a new disease. We need to do multiple different management practices in multiple different places to try to promote forest health. In some areas like that, these urban parks that have a lot of invasive plant pressure, we think it's really important to be proactive and get regeneration right away. But of course, some stands you just want to leave alone and that are in rural forests and see if there's any beech resistance out there. And then another new project that I'm starting this summer that I alluded to a bit with the urban project, but we're trying to do it broader across Connecticut, is once again individual beech tree treatments with this phosphite bark spray that was developed, the idea of which was developed by another scientist at the station. And we're running a lot of different experiments and associated with this, but the applied conservation outcome is that our hope is that we'll help at least preserve some of the beech genetic diversity across the state of Connecticut or regionally with our cooperators to really kind of like buy us time as we figure out what to do with this new disease that has got everyone, like no one knows what to do with it. So at least we can preserve some of the genetic diversity for future projects like tree breeding, etc. So yeah, that's a project that I am setting up this summer of this beech treatment project. We're hoping to have a site at Great Mountain Forest. We're also actively looking for other sites that have at least some replication of beech, and so feel free to reach out to me if you have ideas of potential sites. I will say that we're trying to select sites that have what's called smooth-barked beech because there's another disease that impacted beech called beech bark disease, and if we're going to be treating the beech and trying to preserve genetic diversity of beech, we want to prioritize ones that could be beech bark disease resistant, so we call them smooth or clean barked beech. But yeah, anyway, the takeaway really, which I've hopefully hammered home enough, is that managing for resiliency is really managing for diversity at the landscape scale. There's not one solution. All management practices have trade-offs, and it's really about doing things in different places to try to create ecosystem health collectively across the whole state or region. And I always like to end with some more pretty pictures from the aerial survey, once again, because a lot of my talk veers on the more depressing side, given that there's a lot of forest health issues that we're dealing with. But Connecticut has really diverse forests. We have a lot of forest cover. All of us spend a lot of time, most of us spend a lot of time driving on all the highway corridors and seeing all the sprawl. But when you're in the plain, you see all of the forest, and it's really quite shocking. You're like, that's Connecticut? I thought it was all one big suburb, but no, it's really quite amazing. So we have a beautiful state, we have issues, but there is hope. All right. Thank you so much for listening, and I have tons of collaborators and land managers, including Great Mountain, that I would like to thank, and I'm happy to take any questions. Yes?
Picking up on the concept of soil nitrogen and soil carbon, and the also effect of allelopathic invasion, you talk about how invasive plants can also alter soil chemistry and mycorrhizal.
Yeah, that's a big question and really deserves I could do that talk, but it deserves an entire other talk. But yeah, so one mechanism with which invasive plants can promote their own dominance is by something called allelopathy. So they put chemicals in the ground that only they can tolerate and other plants can't tolerate, and so that's what makes them grow really well. In addition to putting more toxic chemicals in the ground, there's also plants can put compounds in the ground that aren't necessarily toxic, but just that they thrive better under. And so for invasive plants, one mechanism is increasing nitrogen availability. There have been some studies that have shown that by putting in really high quality leaves that have really high nitrogen content, they can kind of facilitate their own spread and dominance. And then another mechanism of allelopathy is putting chemicals in that kill mycorrhizal association, so the beneficial fungi that plants need to grow to once again promote their own dominance. So yeah, I did my master's thesis on invasive plant-soil interactions, so I have lots of thoughts that are probably too many to talk about right now. Yes.
But following on Tom, soil, carbon versus nitrogen, have you looked at all, or could you look at, this was a field for 250 years, this was the field for 50 years, the difference between nitrogen and that seems that age data you could get somewhere else, like the land record, and it might inform.
Yeah, totally. That's one of the reasons I really like using soils in this context and think about how it affects plant community composition is because I've talked a lot about our land use history here and how it was mostly agriculture, and that's what you're referring to. Historic forests that were historically agricultural, they were plowed, they have higher nitrogen availability. There's been a lot of studies that showed that. And we can look at the land use history data to do that, but also just looking at the soil nitrogen availability is a really good indicator that captures that and natural fertility gradients and that, like all sorts of other things. So kind of, in my mind, tells us a little bit about everything. But I love, the land use history super strongly impacts soils and, in turn, plant communities because of that. Yes?
Thank you very much. So 3 years ago, all my leaves left my beech trees. But then last year and the year before, I never had so many little beech trees coming up. Is there still hope? Is that what you're telling me?
Beech is a different story than the ash. So we don't know, basically, is the short answer. And so beech do something that's called sprouting, and so that's why in some of those stands that I showed you, beech is so dense, is because of that other disease, beech bark disease, which historically affected it, which when it stressed out the trees, they resprouted like crazy, and then it became super dominant. And so the trees are stressed, and now they're sprouting in response. It's kind of like a last attempt to survive. But because they're clonals, right? So they have the same exact genotype as the parent tree. That doesn't breed like any kind of resistance to beech leaf disease. You need to have like sexually different individuals in order to actually like have some kind of resistance. So in that case, unfortunately, I would not say it's all that hopeful. Yeah.
Question about your beech tree treatment. What size of an area you're looking for, and how long would this experiment go for if we contract with you?
So I am really looking for a replication of like at least 20 to 40 trees per site of similar size classes. The experiment is probably going to go for like 3 years, although the impacts of the experiment could be much longer.
That's all doable. It's in Norfolk here. I know you'd be working with you. My property is a little bit more accessible this time of year. We'll definitely reach out.
Cool, yeah, for sure.
And see which one it is.
Yes.
At the end of your slide about the emerald ash borer, you had a little, I assume, parasitic wasp.
Mm-hmm.
Did that happen to be a native wasp that happened to like emerald ash? Somebody deliberately imported it.
Yeah.
So
So that's the other, that's the work of the other entomologists, the scientists at the station. And so that's classical biological control where we have this invasive pest that's not a problem in its native range in Asia because there's a parasitic wasp that keeps it under control there. And so when it becomes accidentally introduced here, after doing lots and lots of tests to make sure that it only attacks emerald ash borer and doesn't have other ecological impacts, they then introduce the specialized parasitic wasp here to try to keep the population down.
So that's, to me, a fairly quick turnaround. I mean, because you've done some of the same things with little beetles that attack the woolly adelgids, which I had the sense was a much longer process before you were willing to import the little, whatever they're called.
This is a little bit outside of, because this is like the entomologist field. But yes, like classic biological control is used for hemlock woolly adelgid, it's used for emerald ash borer. But there's lots of, there's entire research programs of like, does it survive in our climate? Like if you release it, will they all just die? Or then you have to release it every single year. And so it seems like such a perfect solution, but then there's lots of little issues, iteratively. So this kind of goes back to, we think it's working, but we need to continue doing this monitoring and use these multiple approaches. Yes?
Have you ever done an association of the nematode and the effect of like the weather changing, the climate change? Or like even looking at the life cycle of a nematode, like once it's in your leaf, you know, like.
Yeah, that's
there permanently and then.
Yeah, I don't study the population dynamics of the nematode itself. There's another scientist at the station, Bob Mara, who does that. But it is something that people are thinking about because this is the map from last year in 2024, the range map. And so you'll see like the northern inland area. Canada has it, but this is developed by the U.S. Forest Service, so it only shows the U.S. But anyway, the northern areas of Vermont and New York didn't have it last year and still didn't have it this year. And so the Forest Service is like testing some initial ideas of whether there's an upper limit to cold tolerance that would kill it off and like therefore slow the spread up in those northern areas. So yes, people are definitely doing it. It's just, yeah.
So then, do you think that the information that's in Canada becomes even more important?
Oh yeah, they definitely work with the Canadian cooperators. It's just this one particular map does not show it. Yeah, lots of unanswered questions, and there's definitely people doing work on that. Mike, how much time do we have? Do you want me to take? All right. Well, I see one more hand, so why don't we take one more question, maybe two more questions. But I can also hang out here and continue to answer questions and not hold the whole audience hostage. Okay, one more question in the back.
Would you be able to speak at all about like emerging or potential threats to our forest that we should be paying attention to, like that are most like you knew that emerald ash borer was coming. What else is coming that we should
That's another talk that I give. So one thing is laurel wilt, which is, so laurel wilt does not affect mountain laurel. It affects plants in the family of Lauraceae, which most notably includes sassafras in our state. But anyway, this was an issue that was causing a lot of problems in the southeastern U.S. and just this year it was detected on Long Island, so just across the Sound, where a bunch of sassafras trees were all of a sudden just like browning and wilting and dying for absolutely no reason. So that's one, is looking at your sassafras, and I mean it'll probably be in southern Connecticut first, given the proximity to Long Island, but that's one we're keeping an eye out for. And then the other big one, also a pathogen, which has been detected in New York but not in Connecticut, is oak wilt, which it primarily affects oaks in the red oak group, and the most distinct symptom is premature leaf fall and browning in like late July, early August. This year we got a lot of questions about oak wilt this year because we had a pretty substantial drought around then that was causing some leaf drop. But that is the most distinct symptom.
Thank you.
All right, I said one more question, so I'll stay up here and continue to answer questions. Yeah.
So let's give Eli a hand.